Start the recording now. I want to record it so that we can save it. That means you can catch all my mistakes and repeat them to yourselves, but also try and work out what each of the pieces are. So after the break, remind me to start the recording again so that we've always got that as some kind of record. Okay. Let's start. So these are basically a bunch of lectures, and all of the lectures are found at that website. Not all of them are up yet, but they will be as we work through it. So before, or in this semester, next 7 weeks, I want to cover an introduction to structural econometrics, and then we'll go to something called summarizing the data. I could have said something like estimators, but if I said estimators, it would be estimators of what? And so before we even get to the point of what it is, I want to emphasize the fact that the reason why we do econometrics in the first place is because we need a way of condensing the data in a form that's intelligible to us. So it's going to involve all kinds of shortcuts about what's important, what's not important, because the most detailed way of explaining the data is to just lay it out. Here are all the numbers. And that is useless because in large data sets, we simply don't have the mental capacity, not even close, to be able to look at a whole bunch of data and then do the analysis in our head as if we were master chess players or something like that. And so when we're thinking about econometrics and when we're thinking about what we'll call data reduction methods, it's premised on the notion that we're pretty stupid. Now, it's not just that we're pretty stupid, it's worse than that. Although we have computers, because they're programmed by us with our software, those computers are also limited. And so that's the sense in which talking about right answers don't make a whole lot of sense. We can try and be internally consistent in terms of logical progression, stuff like that, but that's probably the best we can do. The hope is that we summarize models in the way, or summarize the data in ways that are useful, okay? And that is, when you're thinking about what economists do, you're thinking, I'm going to be employed, or I am already employed to be an economist. I'm producing something that people want to know. There's a demand side to being an economist, and that demand is going to change over time. So, okay, so we think about different ways of summarizing the data. That's going to lead us naturally into a discussion of probability because we're going to be asking the question, how did this data come to be? And it's going to revolve around something called the data generating process. There had to be something to make the data what it is. And that is essentially what we're trying to think about as we explain what the data is. There was something that made it this way. If we could find out what made it this way, well, then we could work from there by asking, well, what if it was something else that made different data? And we would be discussing what I'll call counterfactuals or policy experiments at that point. We've talked about probability in a couple of lectures, enough so that we can move forward on it. Pretty soon we'll discover that using probability in terms of knowing the exact probability or being able to derive the probability is too hard. And so that is going to lead us into saying, although we don't know the probability distribution for this summaries of this data, perhaps we can work out what distributions this probability that the data would converge to if there was enough of it. Now, that is a very loose way of describing what I'm going to call asymptotic theory, but obviously, as we move through the course, we'll be more precise. So three segments to the second set of lectures, which are going to be more application-based. The first will be working through essentially more or less what the profession knows and what the profession does with regards to dynamic discrete choice models. I'm going to explain what a dynamic discrete choice model is in this lecture. Then we'll move on to what is underlying markets. What is market microstructure? How does auctions, financial markets, how do they work? How do we analyze data from these markets? And the third area is going to be on optimal contracting. In the first part, by the way, I mentioned for the discrete choice, we will be including industrial organization types of applications. So not just individual choices, but what happens when firms, I won't say, well, you could say collectively, but perhaps non-collusively, perhaps non-cooperatively make choices. That will also be part of our discrete choice discussion. Now, throughout these lectures, going to imagine the data is generated by a model. And in a way, that statement really means the data is generated by something relatively simple. In other words, there are going to be a bunch of assumptions that if you make, that's how the data was generated. So a model in the world that I'm talking about is just a bunch of assumptions. What assumptions are you willing to make in order to be able to draw inferences from the data that you see? We're going to have to make some assumptions, because if we don't make any, well, then it's just a matter of turning the data over and letting people go from there. Good luck. So that's one thing we'll be doing. When I say data generated by a model, really saying data is generated by a bunch of assumptions. And we're going to embrace what I'm going to call the classical laws of probability and statistics. In other words, we're going to take probability and statistics pretty seriously in terms of what you would take in a standard probability or statistics course. Now, as a general approach to estimation and testing, we're going to assume the model comes from economics. Wouldn't have to. You could imagine that if we knew a lot more about how people worked, because functioned, we would be able to say things like, there are these neurons in their heads, given their experience, given their biological setup, genes that they've inherited. We don't have to worry about optimization. That's what people will do. We get a biological theory to explain how humans work. And in fact, if we talk about other species and other plants, what about plants? When we're talking about growing, we don't, or dying, we never necessarily, living organisms, dying or whatever, we don't necessarily talk about individuals solving optimization problems. And even with humans, sometimes we might talk about, well, the selfish gene. In other words, why people sacrifice themselves for their families, and thinking about how to move from there. So it's not necessarily true that individuals are solving dynamic optimization, let alone other species. We do that as a simplification as much as anything else. If we had an axiomatic theory to explain how people behaved, then we might use that in our econometric problem or to explain the data. So I don't necessarily want to rule that out. The reason why I'm going to take that approach in this course and, you know, all of my research is because, first of all, it doesn't actually require a lot of, well, it requires some assumptions, but you'll see it leaves a lot of flexibility there. And second of all, if we are going to move away from solving dynamic optimizations or thinking about how people best respond, you have to come up with a convincing story of what people do outside of the very specific situation that you're analyzing. In other words, if you come up with a theory that says, well, people will always behave this way in this specific situation, great, you have a theory for that, maybe. But what happens when you change the underlying conditions? How are they going to behave then? If you only got a very specific theory about how people behave in that situation, you won't be able to tell me. And yet, part of the reason, one of the big reasons why we look at data is because we want to explain what goes on when we change the data generating process. So that's the dynamic optimization part. And that leads naturally into a discussion of equilibrium. And we will talk about different concepts of equilibrium and how they apply in these kind of settings. The most natural one is a non-cooperative game setting, but perhaps competitive equilibrium is the easiest one to look at, and that's what we'll focus on first, which is what you would do in principles of economics. And then we start getting a little bit more complicated as we think about asymmetrically informed individuals, individuals with different amounts of information from each other, contracting with each other, what you would expect under those kinds of conditions. And the other thing that we will naturally take for granted in the background, if not in the foreground, is that people are making consumption choices and production choices in competitive equilibrium. So the competitive equilibrium was always a reasonable sort of background situation for other markets that we're not focusing on. But even sometimes when we focus on a given market, we might assume it's in competitive equilibrium, not because we necessarily believe it, but because it provides a fairly simple way of approaching the problem. When you start doing principles, usually you would imagine people were price takers, firms were price takers, and you work out what people would do under that kind of framework. Well, the reason why you do that is partly because it might sound compelling, at least initially might, I don't know. But another important reason is because it's simple. And I've already told you in the first slide, the reason why you start out with data and have to do something is you have to simplify it. And so you're always looking to ask questions, how do we simplify enough to make it tractable so that we can get something useful out on the other side? Because if we simplify it too much, of course, we won't get anything that's useful. So, you know, there's this trade-off. And obviously, as machines get better, as we learn more, well, then we can become more sophisticated. But that's essentially how we kind of think about these things. So first thing I want to do over these next 4 lectures is to give you a flavor of what people do in structural econometrics, okay? And so I'll start off by describing a little bit about what a structural economic model is in discrete choice today. But then for the next 3 lectures, I'm going to give you some examples, mainly 2 toy models, really, and then one that's not really a toy model. And I'm defining toy models by history. So if it's older, it tends to be a toy model because you're using computers that were invented 40 years ago. And if it's more recent, well, then it's more or less using and employing current technology. And I'm not going to expect you to understand everything that I do in these first 4 lectures, sort of in the same way that we develop things later on. At this point, what I want to try and do is introduce you to the world of structural econometrics so that you can see where we're going, and so that you have some understanding of the kind of tools that we'll use, the kind of problems that we can solve, the inferences that we can make, sort of where it all stands. You know, this is a perfect 4 lectures to kind of see, perfect, I don't know, but first 4 lectures to see what, am I interested in this stuff at all? You know, because it'll provide a natural cutoff point for asking whether it's worth going on or not, okay? And that, of course, is entirely up to you. We're very much in the experimental stage here. In terms of the production of these kinds of lectures. This is only the 2nd year that I've done it. It's some kind of oral textbook that I want to use for my own class when I'm teaching, but it's also an oral textbook for Cyprian as he takes his class in Finland, and that provides some sense in which we can kind of cooperate across institutions, and we sort of hope to develop that over time. Okay, what do we mean by this data generating process? The data typically for us, and actually for most studies now, typically can comprise a sample of individuals for which there are records on, say, their background characteristics, their choices that they make, and the outcomes from those choices. So the idea is that as econometricians, to say something useful, we'd like to say, well, what if their background characteristics changed? How would that affect their choices and those outcomes? In other words, we'd be making a prediction of what if the world was a little bit different? We're thinking of introducing a policy. We change taxes or subsidies, change the prices that they face. How would they react? What would happen? That's the kind of thing that economists should be good at. If we can't do that, the real issue to me is, why are people paying us? You could say, well, we are helping to summarize the data in ways that look nice, kind of aesthetic, kind of cute. Maybe people would pay us to do that, but my feeling is not much. The reason why I think economists have value is because they can analyze social behavior in the sense of being able to predict what would happen if the world was slightly different, and so provide a little bit of a guidepost of what is a good idea and what sounds like a terrible idea. Okay, so as we try and do this, what are the challenges to making predictions and testing hypotheses? Well, one of the problems that we're going to run into pretty much straight off is that once you get into a sophisticated, moderately sophisticated world, in the sense of model that is takes a graduate student to understand as opposed to a high school student. Once I'll define that as one metric of sophistication, then they're nonlinear, highly nonlinear, and that makes things quite difficult in terms of both solving the model and also using the data. Okay, so there is the fact that we're dealing with complicated models, and that makes them hard to solve. and it also makes them hard to combine the data with the model to know exactly, if you like, what values the parameters take in that model, okay? That's one thing. The second problem that we face, that the data that we get is not good enough, in the sense that it will provide an incomplete description of what we think is relevant to the problem. Anyone who, and some of you guys have reached that point and apparently already well past that, starts a thesis, anyone who starts a thesis is going to be faced with the problem of what kind of data answers what kind of question. I need to have a good question and good data, notice that technical word good, to be able to explain or get somewhere with it. That's something that economists, for a while, I'd say, I'm saying 50 years ago or more, kind of ignored. There was this notion that we're economists, we are the imperial social scientists, can say something valuable, in fact, give a definitive answer about everything. Well, yeah, we can all talk, but the issue is, how valuable is what we say? And really, we need to be able to, I think, we should be able to provide evidence for what we say, as opposed to just introspect about what I think is important. And so that's going to be based on the data that we have, and the data that we have is going to be restricted. And so the questions that we can say a whole lot about are also going to answer or provide insight in, are also going to be a little bit restricted. That isn't to say we just ignore questions that we don't have any data on. It isn't to say that if we've got poor data, we don't talk. It is to say, though, that if we have poor data, well, we probably have to be a little bit humble about it instead of just saying, okay, this is what's going to happen, because probably we'll be wrong. Economists are notorious in making wrong predictions. So here's our setup. We think about a simple, what I'm going to call a simple standard. How about that? Discrete choice, dynamic discrete choice problem. Let's think about some of the issues that are involved here. Imagine each period, right out to some t, could be infinity, that someone is choosing between cap j mutually exclusive actions. And since they're mutually exclusive and you're choosing one of them, it must be that the jth action is either chosen, that's the one, or not. One of them has to be chosen, exactly one of them has to be chosen. So the sum of these things is equal to 1. So at an abstract level, demanding or requiring that these choices be mutually exclusive is innocuous. All you do is partition the set of choices up so that what I've just said is true. So for example, in a female labor supply / fertility model, where the female is thinking about how much she works and also when she bears kids, we could suppose that she either works and doesn't have a birth, works, has a birth, doesn't work, no birth, or no work and birth. Okay, those are the 4 combinations. By the way, you might wonder why I picked on female labor supply and fertility. It has nothing to do with what I'll call the current political climate. It has to do with the fact that females in most Western countries, in the US and in particular, have much more variation in labor supply than males. And much of that variation is correlated with when they have kids. Okay, the fact when they drop out of the workforce or suspend the workforce for a while is related to having kids, young children. And so if we try to analyze males, we don't get any variation for a start, or not nearly as much variation. And not only that, we don't have as much of a causal factor because, again, studies show that, almost all studies show, that fathers put much less time into their children than mothers. I'm not commenting on whether that's a good thing or a bad thing. I'm just saying that's what the data shows. And so you can see that in practice, it appears that females take this trade-off of how much nurturing kid, how much working, way more, have this way more seriously, in the sense that they substitute between one and the other way more than males do. So you've got the potential of a causal factor, fertility, and whether you work or not, outcome. These are two choices that are made sort of simultaneously, maybe not exactly together. Thing is, doesn't happen with males, and hence there was a whole lot of, in the labor literature, there's been way more study of females than males, simply because there's more variation in the data. And this is coming back to an original point, the point that I made on the slide a couple of, I think last slide, where I said, you got to look at you've got to look at data where you think you might be able to say something. And obviously, if you don't have any variation in the data, because you've really only got one observation, how are you going to say very much in that situation? Okay, so these actions can potentially depend on all kinds of things. Where you are in your doctoral program, what you're planning to do in the future, age, how many children you already have, whether you have a partner or not. All of those kinds of questions come into play, and you can imagine a whole lot of other background variables that might be important. So in this little example, I'm imagining that here are the number of births that you've had before now at time t. So that's just the number of kids you've already got, okay? And here is your work experience. And I'm just imagining that your work experience in the last period and the period before counts. So in other words, these might be how much did you work before? Just in the last period, excuse me. Make these two choices be this one involves work last period. Let's go back a slide. Whoops, went back. Sorry, here we go. Here's one choice where you're working, and here's another choice where you're working. Here, in these choices, you're not working. So did you work in the last period? You're just summing those first two choices, okay? Whether you worked in the last period or not. The idea is that if you have work experience, and in other words, did you work last period, then your wage is likely to be higher. Of course, work experience is not the only thing that work experience, summarizing work experience like this is way too simple, because it's not just work experience last period, but also the period before and maybe a few periods back, and they'll count differently depending on what you did. So this is obviously very simple. Likewise here, these are the number of births that we had. Well, wouldn't it depend whether you have young children or not, or older kids? Because that might affect things too, right? So it's not just the number of kids you've got, but also their ages. So you can see I've got very simple description of background in this setting, okay? Very simple description. And in an application that we would do these days, it's way too simple, but it's good enough to explain some of the concepts that I want to talk about now. And this, when we're thinking about the state, we want it to be compatible with what we'll call this transition matrix. The transition matrix is going to tell you, here's your state today, here are your background characteristics today, here are the choices that you make today, and here's the probability distribution of what the background characteristics are going to be tomorrow. Okay? So that's why we call Z a state. But intuitively, what we mean is background characteristics today plus choices that you make today give background characteristics for tomorrow. Okay? If this can't be explained by those two things, state today and choice today, then we got a problem. We haven't really specified our model correctly. So for example, if we want to keep track of how old kids are or something like that, we have to worry about how they age, because when do they become old? And so they count differently, stuff like that. And then that you have to expand the state in that way. So we'll get to examples of this later. But if there were just, say, 5 mothers had max of 5 kids, which takes into account maybe 99% of the population, and 3 levels of experience, and the number of states, including age, was, say, 50 years, because we might be talking about a horizon of, say, 20 to 70 or something like that, in terms of whether you're going to work or not. Imagine people retire at 70 in Europe, 65 for many institutions. If you just multiply these together, you get 750 states. If you had 4 levels of education, say less than high school, some college, college graduate, which is a pretty standard characterization, and say 3 racial categories, in America, it might be African American, Hispanic, and other, Caucasian, then that'll increase your number to 9,000. In other words, to talk about the number of states, there would be 9,000 different states, just with this very simple model, okay? And so you would have 9,000 possibilities here, 1 of 4 choices, and that will give you what the background characteristics are for next period. So you can see straight out that on the face of it, there are a lot of states, and in this case, since this is a Z by Z transition matrix, given a choice and a time, you got 9,000 squared, you got 81 million cells, okay, in that matrix, 81 million. And that sounds like a lot. Now, in this particular application, though, it's way simpler than that, because the matrix is very sparse. There are only a few things that can happen when you're going from one period to the next. In particular, I haven't allowed for twins or triplets. And so you can only increase the number of kids by 1. And likewise, you can only increase your experience. You either have experience or you're not. You can increase it by 1 or not. And so that is really going to reduce the number of cells that have non-zero entries. In other words, without triplets, of course, the probability of going from 1 to 4 is 0. So you can wipe out a lot of those things. And so in particular, if you look at this pretty closely, there are at most 6 cells you can move between, okay? As we think about, if you start out with W, T, and KT, you can go to these different possibilities in this setup. I've worked them out, because you might not get experience by working, and if you had experience, you don't get experience by working this period, well, then you lose your experience. It's like saying, guys, you get your PhDs now, you don't do research, it dies, okay? Your knowledge dies. So that is a scary thing for academics. Don't want to become a dean because then you're done, okay? That's a, well, so in this setup, there are at most 54,000 non-zero elements, and all the non-zero elements are 1. Okay, so that's a very much different, you know, compare 81 million with that. So in this setup, it is fairly easy, very easy, to work out the transition matrix for what goes on as you go from one period to the next. And of course, once you've got a transition matrix, just to go back here, once you've got this transition matrix, okay, you can ask, well, what will happen after 2 periods if I take action J in period T in period T and action K in period T plus 1? Well, then I just product these matrices together with the K and a T plus 1 version of this for the second matrix, product those 2 matrices, and then I've got the distribution of what will happen 2 periods out, conditional on the choices that I make both in period T and in period T plus 1. Okay, it's a Markov transition matrix. It's a way of thinking about forecasting what's going to happen to the person over their life cycle, conditional on the choices that they make. All right. Now, we can go further than that. I've described this in terms of in terms of a finite background characteristics, but there's no reason to do that. You could go further than that if you wanted to. You could make this a Euclidean space, and then you would have to have a probability density function instead of just looking at probabilities. And with almost this identical notation, we could generalize from the states of the world that occur right now to histories, or even to information known at a given time. Almost the same notation. And why would that be relevant? Well, in health situations, it might be. Something that you did a long time ago, compounded with something that you did recently, might affect you later on. So, and so we could go back even to genetic endowment and stuff like that. But we can imagine that your health state might depend on not just what it was yesterday, but also what it was previous year, et cetera, et cetera. And the notation would change slightly, but not that much. So in this kind of world, although I've very much nailed it down, very much described the discrete setup, where there's only a finite number of things that can happen from period to period, that is really for convenience more than for, because we're restricted that way. And it's important to see that because by learning by learning it for the finite case, the more general stuff falls out pretty simply if and when you do a generalization that requires it. Well, so far I've talked about these transitions that are occurring given a set of actions that people take. How do we model where those actions come from? Because it's the combination of their background characteristics or their histories or their Euclidean states or whatever it is, plus their actions that determine what's going to happen next period. Okay, so how do they make their choices? And we could assume all sorts of things about how people make choices. We need a rule for deciding how people make choices. Where do we get that rule from? And if we had a convincing way of finding out what that rule was, we just plug it in and go from there. And many times that might be a useful thing to do. For example, when we're talking about marketing, we might talk about how the market works when we put on this kind of advertisement or something along those lines. We wouldn't explicitly deal with the individual behavior of each separate consumer buying their packet of detergent or whatever. We would just talk about, well, what happened if we looked at a box of a different size? How would the market behave in this kind of setting? So I'm not suggesting that everybody in our economic model should be modeled individually, because that will make things incredibly complicated. Here we're making choices about what do we view as sort of background, like market background that might react to things, versus how do we think about the individuals? How do we think about the important players in this? So in an individual dynamic discrete choice problem, it's pretty straightforward because you've got one individual making decisions with background, and then that one individual is kind of like playing some video game. What, you know, they stuff coming at him or her, and then they're reacting on their controls. Imagine that's what we're doing in life. We almost are, like remote stuff. But in fact, even when we're doing things that are not remote, it's us as individuals reacting to the environment that we face. And so imagine that everything else is the environment that we face is, we think about it as the F distribution. And in fact, when we go to non-cooperative games, when there are multiple players, we will still do that, but more to come later. Because after all, everybody is best responding to their environment in equilibrium. And so we have to work out how that will play out. Again, more to come. But here we have this individual expected utility. We imagine they're going to live until time period T. Maybe they'll get some kind of value at the end of big T, which might be in this world or the next, who cares? And up until then, they're making some choices. And again, I'm just mapping out these choices being big J each period. Wouldn't make any difference if we had the number of choices depending on the period, or the number of choices depending on the history. I just have to change the notation slightly here, because now J wouldn't be a fixed constant, but it might depend on what had happened up until now. It's fine. And likewise, T could depend on how you live your life. You live dangerously, safely, or whatever. And there could be stochastic rate of death or something. So it's not as if these things are fixed, but for now, let's do that. We're taking an expectation at the front. And what we're thinking about here is that we start out right now with a set of background characteristics. Maybe we make a decision right now in our first period. Maybe that's going to be a given. What happens then? Well, we actually don't know, because there's going to be a transition matrix that determines what happens in the second period. So when we get to the second period, what we do in the second period might depend on not just the choice that we make in our first period, but also what happened, which might not be perfectly forecastable. And so we don't know what we're going to do second period. But we could talk about what we would do in the second period, perhaps, if we could see what the choice, if we knew what was, sorry, once we get there, we will know what we want to do, because it'll be contingent or conditional on what we see up to the second period now. And so we'll make a choice then. There'll be a further transition matrix. Then we will see in the third period what third period's background background looks like. We'll make a choice then. Keep rolling through. Notice what I'm doing is kind of implicitly telling you that the choice that we make in our second period is going to depend on our second period characteristics and what we've done, or actually second period characteristics. Choice in the third period is going to depend on the third period characteristics, et cetera, et cetera. Since we don't know what the second period characteristics are going to be, the third period characteristics are going to be, we don't know what we're going to do, but we do know the distribution of how the z's work. And so we could integrate all of that stuff out, and that's how we would get our expected utility. Again, I'll go through this in more detail as we reach applications. But for now, what I want you to see is that as people evolve through life, they learn stuff if only that their background characteristics change, and then they react to those background characteristics. Now, notice we've got something called the utility that they get out of each of these periods, okay? And that's essentially, what is the utility that I get right now from these set of background characteristics when I take a given action, okay? And so only one of these D's is 1. All the other D's are 0 for a given period. And so if we put a 1 on one of these and 0 on all the rest, we just get the U for that particular J that we put a 1 on. And really, when we're talking about the expected lifetime utility, it'll just track a path of utilities out here, where the path is given by how the Z's change and also the D's change. And you'll get this sum of U's, okay? Follow that? So I've also subscripted the utility by a little t to reflect the fact that maybe at different ages you get different utilities. You like different things at different ages than when you young versus old. And so there is a sense in which I've got redundancy here. Why do I even bother having beta to the t minus 1 when u depends on t anyway? It's completely mathematically redundant, completely. But the reason I put it in there, because I want to make sure that this utility is well defined. We've only got a finite number of things, so this thing has to take a finite value. But I can't sum up ones, for example, 1 plus 1 plus 1, all the way out to say infinity is, or what's the difference between that versus 2 plus 2 plus 2? We're comparing different infinities. That's a problem. So why don't we discount utility to reflect the fact that we care more about the present than the future? Sometimes we discount utility in a big way because we just say, well, t is finite. So it's only up until this number of periods that we even care about utility, okay? Say like 70 or 80 or whatever time we plan to die in this model. But more generally, if we even wanted to compare utilities summed over the lifetime, we have to have some way of making them finite, because otherwise the comparisons between different infinities becomes a little bit problematic. You can do it, but it's hard to work with. And so to make the optimization well posed, not only are we assuming this to be finite, but we're also got discounting here, and that makes this thing bounded by geometric sum, and of course that has a nice finite utility. Okay, so here's our setup. We've got a optimization decision to be made at each period t. You're maximizing this thing by choosing D's each period, where the D's depend on your background characteristics or whatever is relevant. Well, background characteristics. We're going to choose the D's to maximize that. And we will just call the optimal decision rule from that maximization problem, which I haven't really, which I've only intuitively described. I'm just going to call that DT optimal with a little o. And we will let big V denote the value function at this time given your background characteristics as being the expected utility that you get from now on, from t onwards, tau equal to little t right through to cap t, discounted out, of course, when you take these optimal actions and get the resulting utilities. You don't know what those optimal actions are yet. That's not the point. What you do know is that if you arrive at a certain background later on, you know what you will choose then, because you're a good mathematician and you can work it out. Okay. I'm going to argue actually that the people who solve these problems in the data are better than us at working out their problems. I'm going to argue they're better. In other words, the reason why rational expectations is a bad assumption, because it assumes that we're as good, or people are as good as us in being able to solve their problems. I think they're better. And the basic argument for saying that is, whereas we need to sort of get the results right in order to be able to do some econometric inference. And so if we get it a little bit wrong, maybe it won't matter. It's their lives that they're playing with. And we don't have nearly the same incentives that they do in trying to work things out. And so as we think about what people do, probably, if we're going to make a statement about who makes more mistakes, we probably make more mistakes about other people's lives than they do about their own lives. Now, that, of course, is something that we could discuss over virtual coffee, that that is going to tend to be the kind of assumption that I will be making throughout this course. So here's a value function that you get when the problem is solved correctly. And in terms of next period, we could say, well, just turn the turn this into a t into t plus 1 all the way around, discount it by beta on both sides. That's all I've done there. You get that? And so this leads us to what we'll call Bellman's principle, which says that if we imagine that everybody is going to solve their problem correctly from next period onward, here it is, from next period onward, they're going to have a z at this point, a z that's going to be delivered to them by what they do today. See, here's t. You're going to take an action j at this point, and that's going to lead to a new z next period. Next period, they'll be conditioning on that z. We don't know what it is yet, so we're integrating over it, okay? And this thing here, if you stare at it long enough, is just what we saw on the previous page, just this value function right here, next period's value function. And so when people are optimizing, they're thinking, here's my value function this period. If I know what my value function is going to be next period, as a function or as a mapping of what the background characteristic will be, I integrate over that background characteristic, discount it by beta, and then add to that my current utility. When I choose the optimal thing, I will get my indirect utility now. And so, or my value function now. Indirect utility and value function, more or less the same thing. Both are talking about what utility you get when you optimize, okay? So one more slide, and then we'll just take a 5-minute break. To compute the optimum, if t was finite, We just solved the static problem in the last period. It will just be a 1 period problem because going back to here, there's no big V to follow. And so you just be optimizing over these little U's. So just choose the biggest utility. Apply backwards induction. And so once you've got second last period, just go from there. And in that way, you solve sequentially what would happen up until capital T periods if this was finite. And that's why you would solve the model. In that way, you would solve the model. And if in fact T was infinity, well then at the very end, with this beta being less than 1, as you discount it further and further out in the future, it counts almost nothing. And you can apply what's called a contraction mapping theorem. In other words, you can solve the finite problem. And by solving the finite problem, you get very close to the optimum. In fact, it converges to the optimum. So why don't we take 5 minutes break? I'm seeing 11:02 on my clock. Why don't we take 5 minutes break for now and reconvene at 11:07, 11:08, okay? 5 minutes. I'm sort of here though, if people wish to say, engage in some kind of conversation.